the last class, we have discussed about byproduct oven process, where this method of preparing coke is done in a slot kind of coke oven, where it works on the principle of regenerator. These regenerators are basically heat exchanging devices which are located below the ovens, and they heat the air which is coming out from the ambient atmosphere, and they will send that air, heated air, to the ovens for heating purpose. So this will be in the cyclic manner. One will be in the one side of one will be in the heating zone. Other side of the oven will be in the cooling zone. So when one heating chamber is getting heated by the outgoing gases, and the other one starts supplying the heat to the oven. So this is the property of the bricks, the bricks which we are using in the heat exchanging devices. See the coal charging system. In the previous class, we have seen how the charging of coal is happening in the byproduct coke ovens. In non-recovery coke ovens, we used to charge from the front end in a stamped form, whereas in the byproduct coke ovens, the charging of the coal basically done from the top charging holes. There will be a charging car will be there, which moves from one end to other end, and with the help of these charging cars, the charging holes, the lids of the charging holes will be opened, and there will be a hooper which is aligned at the top of, which is aligned to the charging hole exactly at the top of it, and the charging will be done the hooper into the oven. And this charging card moves from one end to other end with help of rails, which is built on the top of the ovens. Now, once we have done the charging of coal into the oven, cooking basically takes place inside the oven by the heat transfer process, and the heat is transmitted from the walls of the oven. Conduction process. Heating chambers will be located both sides of the oven. For each oven, there will be two chambers will be there. So during the regenerative process, one chamber will be in the heating condition, other chamber will be in the on gas and on blast condition. This is how it will work. So whatever the coal which is charged in the coke oven chambers from the top will be get heated up by the conduction process, and this will take place layer by layer. The cooking process takes place layer by layer. The coal layer which is adjacent to the walls of the oven will get undergo cooking process first, and then starts heat starts percolating from the wall to the center. So in this particular picture, you can see the thermal profile of the oven. You can see the width of the oven of around 50 mm roughly. And as we have seen in the non-recovery coke oven process, where the heat is to travel from top as well as from the bottom in the vertical direction, the bidirectional mode. Whereas in the byproduct coke ovens, heat basically transmits from sides. That is also in the bidirectional mode, but in the horizontal process. So that is how you can see, that is why thermal profile is like this. This is the wall surface, and this is the central column of the oven. Okay. And at the walls, the mode of heat transfer will be in the conduction mode. And at the interior part, the mode of heat transfer will be the conduction as well as the convection mode of heat transfer. And as we know, during the cooking process, the volatile matter, whatever is present inside the coal, that will be expelled out and will get combusted. Cooking basically takes place nearly around 12 to 18 hours. This is in general, but it depends upon cooking process, depends upon the dimensions of the coke oven, the width of the coke oven. There is a thumb rule where it takes 1 hour to convert coal to coke of 25 mm thick layer. So this is the thumb rule. Likewise, for example, if you see here, there is an oven which is having width of 450 mm. So accordingly, if you see like 25 mm thick for 1 hour, it takes 1 hour to convert 25 mm thick layer from coal to coke. In that way, if you see, it will take around 14 hours for this 450 mm thick coal to convert into coke. So you can see here the thermal profile, how the temperature is percolating, how the heat is percolating into the oven, and how the temperature profile is varying from the central column towards the periphery of the coke oven. As time is increasing, initially you can see this is the first profile, which represents a condition of the oven after 2 hours. So at the periphery you have 1200, but as you are moving towards the central, the temperature is dropping down, and at the center you have a temperature of around 180 to 200 degrees centigrade. And after 4 hours of cooking process, you can see the temperature at the central column is rise to 400 degrees centigrade. Similarly, 7 hours it is around 600. For 10 hours it is around 800. For 14 hours it is around 1000. And if you see, after 16 hours, the temperature is uniform throughout the oven from the periphery towards the center. That means the cooking process is completed. Now, during this cooking process, the behavior of the coal inside the oven, see, as I said, the cooking coals will undergo different physical transformations along with the chemical transformations. So, if you see the behavior of the coal during cooking process in the byproduct coke oven process, from the periphery towards center of the oven, if you see, the whole layer which is just adjacent to the walls undergo cooking process. That is represented by C, is nothing but coke. And just next to the coke layer, we have semi-coke layer is there, that is represented by S. And just adjacent to that, we have plastic zone is there, which is represented by P. And at the center, you have the coal, which is not completely undergone cooking process. So this is the condition of the oven after a certain duration of time. But as time prolongs, see, the cooking process is undergoing, and the thickness of the coke layer which is forming inside the oven is getting increased compared to the first picture. You can see the thickness of the coke layer is getting improved, and the thickness of the coal layer is getting lowered down. Okay. So in this way, the bidirectional mode in both the ways, both the sides of the oven, this side, left side as well as right side, both the sides of the oven, the cooking is taking place because the heat is transmitting along the walls of the oven towards the center. So at the finishing stage, if you see, after 14 hours or so, after 18 hours, if you see, the entire coal is converted into coke, and you have a small layer. This means this is the central part of the oven is the last one which undergoes cooking process. This is the condition of the coke oven once the cooking time is about to finish. So if you see the temperature profile during this coal to coke conversion, the coke ovens, the temperature which is next to the walls will be around more than 1000 degrees centigrade, and the temperature adjacent to the coke, that is in the semi-coke condition, when the coal is in semi-coke condition, there the temperature will be around 600 to 800 degrees centigrade. And similarly, in the plastic region, it will be around 400 to 600. And at the control column, the core part, there the temperature will be around 400, less than 400. So what is happening during this cooking process inside the oven, if you see, as far as the temperature, as per the temperature is concerned. So from 0 to 300, the moisture content will be removed, and a certain amount of volatile matter also will be expelled out. And when the coal attains the temperature of around 400 to 500 degrees centigrade, then it will convert into plastic mass. And slowly, once it attains a temperature of 600 degrees centigrade, that will transform from plastic mass into semi-coke. And between 600 to 100 degrees centigrade, the semi-coke will convert into a completely porous, a densely porous mass that is called coke. So during this conversion, the most important phase is the plastic stage. When the coal is solid, the gases moves out when the cooking is taking place. But when it comes into plastic, the evolution of these gases will get restricted, and this restricted gas, due to high plastic layers, may cause pressure on the oven walls. Not desirable. Further, if the plastic mass is too liquid, and it may come out along with gases on the top of the coal bed as froth, and that will get solidified on the upper zone of the oven, which is exposed to high temperature. Then that solidification of the froth will yield sponge coke. This sponge coke will have very less strength, and this will show a great impact on the total strength of the coke. We'll see the charging and discharging sequence which you basically follow during coke making process. As I said, that a series of ovens, we call it as one battery. So when you are charging these coal into the ovens, we cannot do either charging or discharging of the coal into the ovens one after other. Means any two adjacent chambers, you should not do charging or discharging, because opening of the doors of the any two adjacent ovens will cause a heavy thermal demand. There's a huge loss in the temperature, and that will certainly lead to thermal shocks, and it will damage the refractories present inside the oven. That's why we give a proper distance between the ovens for charging and discharging. So all the charging and discharging is done keeping a good gap in the running or fresh oven. So here we basically adopt P plus method. That means if you consider a 40 oven battery, then the sequence of charging would be, if you have charged in the first oven, then you need to charge in the 11th oven, that is 10 plus 1, 11th oven. Then we have to leave again at least 10 ovens, and we need to charge on the 31st oven. Like that, we need to give a gap of at least 10 ovens to avoid this thermal shocks. After charging 31st oven, then the next oven to be charged would be 4th oven. That is the 3 plus 1 sequence, which is nothing but 4th oven means here we have charged first oven plus 3, 1 plus 3. That will be the 4th oven. Followed by 14th oven, that is again 11 plus 3, 14th oven. Followed by 24th oven, that is 21 plus 3. So this plus 3 method you need to follow during charging as well as discharging of the oven to avoid the thermal imbalance inside it. Whatever the sequence we are following for charging, the same sequence we need to follow for the discharging also, because the one which is first filled will be first get completed cooking process. So once the cooking has done, as we have seen in the previous classes, the entire process of cooking making through a small short video. The same process we adopt here also for the charging of the coke. But the only thing is that the dimensions of the plunger. In the previous video, we have seen the plunger is horizontally is extended as per the width of the oven, and we are trying to push it. But here, as dimensions of the width of the oven is very small, so the plunger is also will be exactly as per the height of the oven. We used to push with the help of a plunger, having extending vertically. That will be pushed from one end to other end. The other end of the oven, you will be having the quench car, and the entire coke will be collected into the quench car. And once the oven is empty, again the charging will be done from the top. And whatever the coke which is collected in the quench car, that will be subjected for the quenching process. So here, in the previous video, we have seen when we are discussing about non-recovery coke oven process, we have seen the wet quenching method, where water is the media, quenching media. There are basically two methods are there. One is wet method, other one is the dry method. So wet method, where we use water as a media, and these quench car will be subjected under the, moved and kept under the quench tower, and through the water pipes, the water will be sprinkled on the red hot coke, and that is how the coke will get cooled down. But here, one disadvantage is that during this quenching process, the amount of heat which is extracting out, so which we cannot recover that. So there is a huge loss of heat, and also there is a huge fusion, which we have seen in the previous video. So if you see, the heat energy is basically lost when there is around approximately 1 gigajoule per ton of coke. So that will be nearly 240 kilowatt hour power for every ton of coke. So if we could able to extract that heat, if we can able to capture that heat, we can produce that much amount of power. So the advantages of wet quenching is that it is easy to operate, and low cost is involved. There is no need of much huge equipment is required for this process. The limitation, the disadvantages are it consumes large quantity of water, it creates a huge air pollution, and there is a huge loss of thermal energy also while quenching. And certainly, you're using water as a media, so water will be get percolated into the pores, into the internal pores of the coke. So it takes some time to convert into wet process before we, or either we need to use some other equipments for drying this coke. So it cannot be readily used as a charge material in plastics or any other process, unless until it is completely converted into dry coke. The other method is dry quenching method. So here you can see this is the picture which represents the dry quenching process, where you have a chamber for the dry quenching, Here we are using either air or nitrogen as a quenching media. Um, so here what we are doing is that from the top, from one end, from here, we are basically charging the coke, the red hot coke, fed into this chamber, and you have airtight doors are there. That will be, once the charging is done, that will be closed, and air or nitrogen is circulated through this uh, hot coke, cool down. You can see from the picture, there's a blower from the bottom, so which to pass air, nitrogen, yeah. And then whatever the heat which is extracted out during the cooling process, that is collected, and that heat is allowed to pass through uh, boiler pit. Water circulating pipes are there. So this is the WHR waste heat recovery boiler, where this heat is allowed to fall onto these water circulating pipes, where the water converted into steam, and that steam is used for the power generation. So this is one of the biggest advantage of using dry quenching method. And the by this method, whatever the coke which is cooled down to around approximately 400 degrees centigrade will be discharged out, and that will be used for the various processes within the integrated steel plant. The advantage of using this dry quenching method is we can recover the maximum amount of thermal energy associated with coke, and we can deliver dry coke which can be readily used in the integrated steel plant, and we can avoid air pollution because it's a closed chamber, so there won't be much emissions, and we are not using water, so we are using air as a media, cooling air or nitrogen. So uh, by this method we can avoid maximum amount of emissions. And yeah, water we are not using as a media, so we can save some amount of water for this. But the biggest disadvantage, or we have very one limitation, is that it is little, comparatively, it is little costly process. Now, um, as the name itself, it is reflecting that um, the byproduct oven process. That means apart from the major output, that is the coke, um, from the off gases which is emitting out from this oven, with that we can also recover some secondary products. So those are like for 1 ton of coal, whatever that is coal, for 1 ton of 1 ton of coal, whatever we are charging in the oven, so we will get around 750 to 800 kg, means around 80% of the coal is converted into coke. So for 1 ton of coal, we'll be getting around 800 kg of coke, and which we can use it for the blast furnace heat as a fuel, and around 45 to 90 kg of coke grease. This is below 6 mm size coke, and around 85 to 345 meter cube of oven gas that can be collected. And apart from that, we can also collect around 27 to 34 liters of tar and 55 to 135 liter of ammonia and around 8 to 12.5 liter of light oil. So these are the byproducts which we can recover from this making process. And this is the advantage of producing coke with byproduct coke oven process. And the disadvantage, the limitations are, so this is comparatively among all the various departments which we basically have in the integrated steel plant, this department, the coke making process, one department is one such, is having highly polluted area, and a great care need to be taken during the operation as well as during the maintenance, because whatever the byproducts which we are recovering during its transportation also, we need to take utmost care, because any of leakage or something like that, if it happens, that will cause damage to the mankind. So this is utmost important, utmost care one should take during this making process, byproduct recovery also. Stop it here. Next class we will see what are the testings which we need to do for the coke. Till now we have discussed about two methods of coke making process. One is through the non-recovery coke oven process, other one is the byproduct coke oven process. So any one method can be adopted as per the availability of the resources. Some of the plants, they will be having a byproduct coke making process. In some of the plants, they will be having non-recovery coke oven process. Whatever it may be, the end product will be the porous coke obtained after coking. The metallurgical coke, whatever it is obtained through this process. Before we subject this metallurgical coke into the blast furnace as a fuel, we need to do some testings, quality testing, quality assessment we need to do to understand whether the coke will sustain those environments, whether it can undergo proper combustion or not in front of the tuyeres, whether it is having good strength or not. So these kind of whether it undergo production or not inside the oven. So these kind of testings we should do before we subject into the blast furnace as one of the raw material. So this part we will discuss, the testings part, the coke quality assessment that we will discuss in the next.